Hi everybody. So the next part of this topic on modern physics is about atomic spectra, and in order to understand that, this is looking at if you take a diffraction grating and you look out of the window through that diffraction grating, what you're going to see is a complete spectrum. And this complete spectrum is, I don't have all the colors, but you have red at one end and blue or violet at the other end, and you can see that one color blends into another. Okay, so that is because white light, it consists of 7 colors, and these colors all diffract at different angles when they pass through a diffraction grating. However, if the light is not white, but if it is the light given off by a heated element, so you know that if you heat gases or any element, they give out light, but that light is not white, but it's particular colors. And so if you look at, this is what we did in the class, I gave you spectroscopes, and when you looked out through the window you saw the continuous spectrum. When you looked at through the spectroscope at the tube light, you saw definite lines. Those definite lines are called discrete lines. So it was no longer continuous, but what you saw was lines. And so if you see the light emitted, colored light emitted by a hot gas, what you get is an emission spectrum, which is colored lines on a black background. And this is what you saw. Okay, so you have the red, the green, the blue, and each element has its own signature spectral lines. What I've drawn is something, the spectrum for hydrogen looks something like that, but the spectrum for neon is quite different from the spectrum for sodium or mercury. So it's almost like how we have a fingerprint and a signature, which is only our own, and nobody else has the same fingerprint or signature. Each element has its own fingerprint or signature spectral lines, and that is how you identify elements, and that's how we know what gases the sun and the stars are composed of. Okay, so as opposed to the emission spectrum, you can also have the absorption spectrum. So when you get an absorption spectrum, when you pass white light through a gas, it is found that the gas absorbs particular frequencies. So you have this colored background, but you have some parts of it missing. So you might have, and for the same gas, what is present in the emission spectrum is absent in the absorption spectrum. So the lines coincide. And this is what puzzled scientists for a long time. And so a lot of scientists did a lot of studies with this, and one of the people that we're going to be looking at is Balmer. He was a Swiss mathematician, and he studied the spectrum of hydrogen gas, and he chose hydrogen because it's a simple element with just one electron, and they knew this emission of light had to do something with electrons, and they were trying to figure that out. And you know how every light, every color has got a particular frequency and wavelength. So what Balmer did was he studied the hydrogen spectrum. It looked something like this, and Balmer went a step further. So I just rub out one of these, and he gave these lines numbers. It may not make sense to you now. He was a mathematician, so he played around with numbers and it made sense to him, and he could come up with an answer for the wavelength of these lines. So he called this line number 3, 4, 5, 6, and after that the lines really got really close together, so he couldn't differentiate between the two, and he came up with the formula for, so that's Balmer. Okay, so Balmer's formula for the wavelength, which is 1 over lambda equals r times 1 over 2 squared minus 1 over L squared. So that's Balmer's formula, where lambda is the wavelength and r is what is called Rydberg's constant. It's a constant, and the value for that is 1.097 times 10 to the power of 7 per meter. And you wonder why he's put 2 squared, but it will come, you will know why it's 2 squared and not some other number in a little while. L stands for the line number. Okay, so if you wanted to find the wavelength of line number 3, so you go 1 over wavelength, you substitute for r, 1 over 2 squared minus 1 over, if it's line number 3, it's going to become 1 over 3 squared. And then if you find the 1 over, that answer, you get wavelength. And if you know wavelength, it's possible to calculate frequency by using speed of light is equal to f lambda, where c is 3 times 10 to the power of 8 meters per second. Okay, so c divided by lambda will give you frequency. So it's possible to get frequencies and wavelengths, and he was very happy because he found this out. Now, over a period of time, so what Balmer saw was actually what was in the visible part of the spectrum. So red and blue and green, this is all visible light. But as they got more sophisticated instruments, they found they could see more of the hydrogen spectrum, things that are not part of the visible light. So there was Lyman who discovered the ultraviolet part of the spectrum in the hydrogen atom, and then there were people called Paschen, Brackett and Funt who discovered the infrared parts of the spectrum. So they modified Balmer's formula and they called it Rydberg's formula. And the difference between Balmer's formula and Rydberg's formula, which is the generalized formula, the only difference is instead of 1 over 2 squared, they've got 1 over s squared. Okay, so what does the s and the l stand for? So they came up with a whole lot of series, where s is the series number. So I'm just going to draw a table over here. So that's the formula. I'm just going to rub the board because it's a very small whiteboard I have. So this is the name of the series. This is the part of the spectrum. And this is the S value or the series number, and that's your L value. So the first at the top of, even though he was not the first person to discover, we got Lyman at the top because the part of the spectrum that he discovered was ultraviolet, and the series number is 1. And the L value is always at least 1 more than S, so you go 2, 3, and so on. And the next one is Balmer. Balmer is the one who discovered it first because this is in the visible part of the spectrum. His series number is 2, and the L values, it's always 1 more than the series number. And then you've got Paschen. Now, the next 3, they all discovered things in the infrared part of the spectrum. Paschen, Brackett is also infrared, series number 4, and then Funt is also infrared. Now you might wonder why there's so many infrared. The thing is, infrared is not just one particular frequency, it's a range of frequencies. So each of them saw infrared in a different part of the spectrum. Okay, so what does this all mean? And this is when Bohr came up with his model of the atom. So let's look at Bohr's model of the atom. So Bohr was a student of Rutherford. Okay, so you remember in year 12 we learnt about Rutherford, where Rutherford came to the conclusion that the atom has a central nucleus with protons and neutrons, and he didn't quite know what to do with the electrons. He did know that the atom as a whole was neutral. So what Rutherford said was that the electrons orbit the nucleus. But in theory, if something is going in a circle, then it is accelerating and it should losing energy, and the electrons should actually collapse into the nucleus. But this doesn't really happen. So Bohr came up with his model to say that the electrons, yes, are outside the nucleus, but what they do is they occupy different energy levels. So an electron can jump from one energy level to the other by absorbing a photon of energy. A photon is a packet of energy, and the energy of a photon is related to its frequency by E equals hf. And it doesn't, when it absorbs a photon of energy and jumps to a higher energy level, we say that the electron is in an excited state. It doesn't stay in that excited state for too long, but it drops down to what we call the ground state, which is the energy level closest to the nucleus. And when it drops to the ground state, it doesn't need as much energy. And so what it does is that it emits a photon of energy. So in the next video, I'm going to elaborate more on what happens when with this electron energy transitions, and we're also going to learn how to calculate the energy at each of these levels. So I hope that made sense. So bye for now.